And here we go. All right. So he's going to show you now, finally, how to actually see this happening.
Bonding, which is going to be where orbitals overlap. If we have more pi bonding, we're going to increase these. And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase?
Okay. So you have a helium atom. There's your nucleus, 2 protons, 2 electrons. And there's another helium. So as the 2 helium atoms come near each other, the electrons, because they're constantly moving, kind of orient themselves to create partial charges. So one of these, I forget which one, the electrons go away from the atom, and the other one, the electrons go towards it. And what that creates is opposite charges, but it's a partial charge.
It's going to be these London dispersion forces. So right here I have 2 helium atoms, and so they're going to have 2 protons on the inside, 2 electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate.
So, you're going to draw this in a second, but if you have one atom here, this atom's electrons are over here, this atom's electrons are over here, all right? Think about the, let's say we draw a line down the middle of these atoms. One side's going to be partially negative, one side's partially positive. Who can tell me which side of this atom, this one here, which side is partially negative? This side, right? So that's partially negative. What about this side? Partially positive. What about this atom, the other one? Same exact thing. So, what did that create? It creates a positive, negative, a partial positive, partial negative attraction. That's a dispersion force. So he's going to show that. Where am I? Back.
What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are 2 what are called temporary dipoles.
Okay, draw that, please. And actually, I want you to put in the E negatives. So, kind of, I drew the same thing basically. So, draw what I have or what he has, it doesn't matter. But put the E minuses over here on the left side. And then draw your partial negative, partial positive. Draw that dotted line between them. This is happening right now in your body, in the air, in this paper, everywhere. This is constantly happening. Everything has dispersion forces. But it's extremely weak. So this is going to break and form, break and form. And I use the analogy of shaking hands. I could go around shaking hands with all of them. But I'm not going to shake someone's hand the rest of the day. Right? We have to move on and do things here. That would be weird anyway. But the point is, that's a great example. You temporarily shake someone's hand, then you let go. That's exactly what this is. So these 2 are shaking hands, and then that's going to break. And then they're going to shake hands with another helium. And they're going to break that. And they're going to shake hands with... So it's constantly moving. That's partly why gases are always moving. Because the forces are breaking and weakening. Breaking and forming. Okay.
They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those 2. It's fairly simple. It's going to hold them together. Now it's just instantaneous, it's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that.
Right, so if you have literally trillions and trillions and trillions of atoms, then it can be pretty substantial, right? But it is pretty weak. He goes into stuff we don't need to know, but this is what I was talking about earlier. This is kind of more like a straight line or like a rope. Is the way I think of it. So these, when they come together, are more like your palms, and then this looks more like a ball or a sphere. That's like your hand, your fist, right? So fists have less contact area than your palms, right? So that's what he's going to talk about. But we don't need to really know that for the region. So what do you need to know? This. So on your homework, when you go through the 9 molecules, any of the molecules that are non-polar, this is what I want you to draw. Right? So if on your homework I gave you O2, I didn't, because I'm not going to give you one that you have to do, but if I give you O2 on the homework, what you would do is you would say, all right, it's nonpolar. What's nonpolar mean? Oh, it uses dispersion forces, right? So hopefully that's starting to make sense. You're relating those 2 terms. And then you have to draw it. So you would do this. You would say, all right, here's an O double bonded to an O, but now this oxygen, dot, 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 is attracted to another oxygen. And why? Because this is partially positive and that's partially negative. So essentially you're drawing this, and that's what I want you to do on the homework for dispersion. All right? So I'm repeating myself a lot. I feel like I'm trying to go slow. This is what I need you to show me on the homework, and this hopefully will help you understand what the heck dispersion forces are. And again, it's because the electrons are just randomly moving at any given time. When they get close enough, they all kind of migrate to one side, creating these temporary charges, temporary dipole. All right, so that's what you're going to do for this part on your homework. Okay. This one? Yep. Okay. So we're done with dispersion. This is dipole. So write in your notes, dipole interactions, and then copy that down. I literally spend like 3 minutes on this, then we move on. You just learned everything you need to know about dispersion, and that relates to all the other forces. So dipole interactions, also called dipole-dipole, are stronger than dispersion because these, it looks literally it looks the same, right? Is what we just drew, partial negative, positive, dotted line, but these are permanent. Or I should say more permanent. So because HCl is a polar molecule, it creates these partial negatives and partial positives, but the H is always partial positive, and the Cl is always partial negative, always, because they have those dipole moments because Cl has a high electronegativity. So everything you already learned, I know it was before break, it's important to remember that, right? Remember the bonding and why the heck does it have a dipole? Because it's polar. And now, if you understand that part, if you take one polar molecule and bring it near another, they're going to have what's called a dipole force between them. That's the dotted line, so there's your dipole interaction. All right? And again, these are more permanent. They still can break a lot easier than ionic and metallic bonding, let's say, but it's still a lot stronger than dispersion. All right, so that's just one example. So what are we writing in our notes? We're getting that down, and we're also putting put a star here. This is for polar molecules. So non-polar molecules have dispersion. Those are really weak, and those have temporary partial charges. Polar has more permanent partial charges, so therefore it uses dipole interaction. Again, I don't really have time to reteach everything, so I'm hoping this is making sense and you say, all right, I remember this. So it's polar because it has a dipole, which is why it uses dipole interactions. So it's all kind of one and the same. Just the big difference, again, look up here, big difference. This line here is a polar covalent bond. The dotted line is the dipole force. That's two different things, right? So if I take these apart here, right, it looks like this. So that's what it looks like, right? So there's your HCl. It's the attraction between them. That's the dipole interaction, not the stick. That's the bond. That's totally different. Okay, so that's dipole interaction. And I'm done with that. Because we've already learned about polar bonds, polar molecules. We've already learned about all this. So I'm just giving you the information, what the heck is the dipole interaction. That's just one example. Homework's going to practice more. Okay. Next, hydrogen bonding is the strongest. Hydrogen bonding. Alright. So, that would be this one. It's kind of a blurry video, but it's pretty good, so I'm going to...
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom, such as nitrogen, oxygen, or fluorine.
Okay, that's the first thing I want you to write down. Put a star here. Only occurs between molecules that contain H, so hydrogen, with, and underline with, like 5 times. It has to be hydrogen with nitrogen, oxygen, or fluorine. Those are the only three elements that hydrogen can do hydrogen bonding with. So the three they show here, HN, HO, and HF is exactly what I'm talking about. So, the biggest thing kids have a problem with, hydrogen gas does not have hydrogen bonding. Kids have a hard time with it. Why? Because the name hydrogen, right? If this is hydrogen gas, let's say, this is non-polar, so what does it have? Dispersion. It doesn't have an N, an O, or an F. It only has two H's. That doesn't qualify. All right? Why? She already said it, but we're going to write it in our notes. The reason it has to be these three, besides CL's a little special, but these three have the three highest electronegativity on the chart. So the reason it's N or F, this is due to high electronegativity of N, O, and F. So what you drew as the warm-up, you're going to do the same thing for homework. I think water is on there, because that's important. That's the one Regents always asks you to draw or talks about, so we practice that multiple times. But the warm-up is exactly what we're going to put here in our notes. All right, I'll use a different one, different molecule, but you already did this.
In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attracted to the partial negative charge on the fluorine atom of a neighboring HF molecule. Although hydrogen bonding is a type of dipole-dipole interaction, some hydrogen bonds more closely resemble ion-dipole attractions in
Now she's getting squirrely. What do you notice? I know this is really blurry. All three forces, you see those weird little symbols, right? Partial positive, partial negative, partial positive, all of them. Dispersion has them, dipole has them, hydrogen bonding. Hydrogen bonding is dipole, it's just stronger. It's a stronger form, so it is confusing, I get that, right? It sounds like I'm saying the same thing 3 times. But dispersion is really, really weak because it's non-polar. Dipole is stronger because it's polar, and then this is even stronger because it's N, O, or F. So draw that in your notes. That's your hydrogen bond. It's between, so I'm just going to label that, there's your H bond. Okay? It's between the H of one and the F of the other. This morning, in the beginning of class, you did the H of one and the O of the other for water, right? The only one we haven't done is nitrogen. It would be the H of one and nitrogen of the other. And I think the homework, I give you that one somewhere. Yeah, I do. So we'll talk about that tomorrow. So all three forces use those dipole charges here, your partial charges. It's just a little bit different how each one forms. Okay? All right. We're not done yet. Stay with me. So that's it for hydrogen bond. Last one, molecule ion, or ion dipole. You've seen this before. So, molecule ion attraction, put that in your notes. Anytime you dissolve ionic compounds in water, this is what happens. You put salt in water, this is what happens. You've seen this before. I've had you do warm-ups on the whiteboard before. We're going to do it again. So this is ionic dissolved in H2O. That's the molecule ion interaction. The ion is the Na+, for example, and the molecule is the water. So for example, again, NaClAq. Humor me, just copy down what you see there. All right. Actually, I don't like the way they do that. Let's just draw 4 of them. So you have Na+, the oxygen is going to face the sodium ion because oxygen's partially negative. So again, there's that partial negative. It's like the same thing over and over and over. Hopefully you're starting to see that. So there's your sodium, and now your Cl- is surrounded by water as well, but it's gonna be the hydrogens that face the Cl. I don't have a picture for that. So the hydrogens are gonna be facing the Cl minus, and that's because the hydrogens are partially positive. And again, opposites attract. Just like all the forces, it's the same, opposites attract. So this should make sense. You should already be good with this because we talked about this a bunch of times already. And that's why salt dissolves in water. Like dissolves like. There's a similar charge there, right? Opposite charges will attract each other. So there's your molecule ion. This one's really strong. But not that strong. Why? If you evaporate the water, it goes away, right? So water goes away and salt reforms. But it is strong enough to allow it to dissolve in water, break apart. Does anyone remember what that's called when you take two ions and rip them apart? It's not dissolving, it's close. Dissociate. That's called dissociation. You dissolve this in water, it's called dissociation. Alright, I guess we'll stop. I only got a couple minutes. So, take all that information, do the homework, and then we'll go over the homework. Discombobulate. Well, kinda. You guys have a wonderful day. Some of you I will see.